Hey everybody, this is Professor Price coming at you with another example of a proof. Problem number 9 in chapter 0 asks us to prove that if a and b are integers and n is a positive integer, prove that a mod n equals b mod n if and only if n divides a minus b. This is an example of a biconditional statement. It's the conjunction of two conditional statements, namely, if a mod n equals b mod n, then n divides a minus b, and if n divides a minus b, then a mod n equals b mod n. So in order to prove a biconditional statement, we actually need to prove two statements. So let's prove the first one first. So we're going to start by providing a proof of if a mod n equals b mod n, then n divides a minus b. So here's how that's going to work. I'm going to give a direct proof. So I'm going to assume that a mod n equals b mod n. So this says that if I have a being divided using the division algorithm by n, I have a equals sum q1 times n plus r, and if I have b being divided using the division algorithm by n, it equals sum q2 times n plus the same r. The remainders will be the same using the division algorithm. So here, q1, q2, and r are all integers. And also, 0 is less than or equal to r, which is less than n, because n's what's being divided in. All right, so now I'm going to look at the difference between those and observe that n divides that. So a minus b, that's going to equal q1 times n plus r minus q2 n plus r. And that's going to equal q1n minus q2n, which is n times q1 minus q2. So that's of the form n times some integer. So therefore, n divides a minus b. So we've proven what I call the forward implication. If the thing on the left-hand side equal, then the thing on the right-hand side. All right, so now I want to prove the reverse implication. If n divides a minus b, then a mod n equals b mod n. So we're going to give a direct proof. So we're going to assume that n divides a minus b, and we're going to write both a and b using the division algorithm dividing by n. So a is equal to sum q1n plus r1, while b is equal to some q2n plus r2. So here all these guys, q1, q2, r1, r2, are integers. And also I know that 0 is less than or equal to r1 and r2, and they're both less than n. Now I need to assume, and I can, that one of the remainders is bigger than the other. So I'll assume that R1 is bigger than or equal to R2. Okay, so then let's look at the difference. A minus B equals Q1N plus R1 minus Q2N plus R2. And this is equal to, when I do a little rearranging, N times Q1 minus Q2 plus R1 minus R2. So since 0 is less than or equal to R2, which is less than or equal to R1, which is less than N, R1 minus R2 is going to be between 0 and N as well. So this means that in order for N to divide this entire thing, R1 minus R2 is going to need to be 0. So since R1 minus R2 equals 0, this implies that R1 equals R2. And this is the same thing as saying that A mod N is equal to B mod N. Since the remainders ended up being the same, they equal the same thing modulo N. And now that we've proven both sides of the biconditional, we are done.